This is problem set 4, exercise 3. And in this problem is related to closeness centrality. They tell us that we have to consider an undirected tree of n vertices. Okay, so here we have this is a network, which is a tree with n nodes. And now we see here that there is a particular edge that joins vertices 1 and 2. And this edge divides the tree into two disjoint regions, okay? And this region, okay, this region on the left is going to have n1 nodes, and the one on the right is going to have n2 nodes. And they ask us to show that the closeness centralities of C1 of nodes is 1 and 2, okay, which are C1 and C2, are related by this expression here. So this is what we are going to do. So let's see first what is closeness centrality. Remember that closeness centrality for every node was just the inverse of the average distance of every other node. So this is going to be like n minus 1 divided by the addition of all the distances between node I and the rest of the nodes in the network. Okay, so that's the idea, which I can write like 1 over the average of di. That's it. Okay, so this is the expression that we are going to use. In fact, since here what I see is the inverse, what I'm going to do is to write 1 over C1 and then 1 over C2. Okay, so 1 over C1 is going to be the inverse of this expression. Okay, so it's going to be actually the average distance from node 1 to the rest of the nodes. Okay, for all nodes j different from node 1 of the 1j divided by n minus 1. Okay, so this is the expression. Now we can see that we are going to have two different sets of nodes, the ones that are here and the ones that are here in each of these two sets. So for the ones that are on the left, well, it's just the usual. I'm going just to write, I'm going to say that these nodes are going to belong to the set of vertices V1, okay? And I'm going to exclude, so here are the nodes that are in the set of nodes V1, and I'm going to exclude one from this set, okay? So V1 would be every node except this one. And here we would have exactly the same. So here it's the set of nodes which belong to V2. And 2, again, is not going to be included here in this set. That's the idea. So now if I want to write this expression, this expression, what I'm going to do is to separate this addition, okay? This addition I'm going to separate on the one hand the nodes that are on V1, and on the other hand the nodes that are on V2 plus node 2. So this is what I'm going to do, okay? So now we have the addition for all the nodes that are in V1 of D1i plus the addition for all the nodes that are in the set of nodes V2 of D1i plus node 2, because node 2 is not in V2. So, but I know the distance, because the distance between nodes 1 and 2 is given, it's just one step. So in this case, it's just 1, okay? And I still divide this by n minus 1. So this is 1 over n minus 1, and then, so this part is going to be the same, okay? The nodes that belong to V1, the distances here, plus the other distances to the other nodes, the 1i also, yes. But I'm sorry, but no, I forgot, because these distances, since they are, I mean, there is going to be a relation between the distance of every node that is in this set and the distance, I mean, in this set and node 1, and also in this set with respect to node 2, okay? Because clearly we are going to see that the distance of every node here, of every node in V2 is going to be the distance to 2 plus the distance from 2 to the others. Okay, so that's the thing that I'm going to use. So the distance, the second summatory is going to be for all the nodes that are in V2, this is going to be of 1 plus the distance from 2 to I. Okay, so here I changed. This is the distance from node to I, and these are the distances from node 2 to I. And I added here this plus 1, because they are separated by one more step. Okay, so, and then I have to write the plus 1 there. So I have the plus 1, and that's it. So if I rewrite this, now remember that this part over here, this is the summatory of all the elements of 1, of all the elements that belong to V2, and remember that number 2 is not included, okay? So this node is not included in V2. So the number of nodes that are in V2, how many? How many are there? They are going to be n2 minus 1. So this is going to be equal to, okay, so here I have the 1 over n minus 1, then I have this summatory, which is going to be exactly the same, 1i plus, I have this n2 minus 1, okay, which is the addition of 1 for all the nodes that are in V2, plus the addition for all the nodes in V2 of d2i, plus 1. So this one and this one, they cancel out, and in the end what we have is this expression, 1 over n minus 1 of the addition, the summatory of I in V1, d1i plus V2 d2i plus n2. Okay, and we know that this is true for 1 over C1. Now, if I repeat exactly the same steps, if I repeat it for 1 over C2, so now I'm going to write over 1 over C2. This is going to be the same as 1 over n minus 1, just like before. And now I'm going to have here, I will have to count. Now for the nodes that are in V1, I will have to count 1 plus all the nodes that are well, this 1 is the distance from 2 to 1, and then for all the nodes that are in V1, and the distance from 2 to I, plus the distance in V2, the distance from 2 to I. Now, okay, this is exactly the same expression as here, but now in terms of centered at node 2. Okay, so now we are focusing on this node. So this is the node that I'm focusing now. Now we have that on the left side, okay, the set of nodes of V1. This distance, I can write it just like before as the summatory of I belonging to V1 of 1 plus the distance from 1 to I, just like before. Okay, and here I have exactly like before. And 1 over n minus 1, and here I have exactly the same as before. Now the addition of all the elements, of all the ones here for all these terms in this summatory, this is going to be n1 minus 1. So I have 1 plus n1 minus 1 plus the addition for all the vertices at V1 of d1i plus the addition of all the vertices at V2 of d2i. This is an I. And that's it. So these two cancel out. And in the end, we obtain a very similar expression as the one that we obtained before. And 1 plus summatory of I belong to V1, d1i plus. Okay. Okay, so this is the final expression. And you can see that we have, on the one hand, this part here on this expression, and this part here on this expression. So what I can do is to express this expression in terms of the rest. So I'm going to express this summatory in terms of C1, okay? So I'm going to write this like the vertices that belong to blah, 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 okay? belonging to V2, D2I. And I am going to put this, so I have to multiply everything by n minus 1. So I have n minus 1 over C1 because I'm going to put this, I'm sorry, I have to multiply this on the left by n minus 1 and then I have to subtract n2. So that's what I'm going to do. So this is equal to n minus 1 divided by C1 minus n2. And now if I repeat the same calculation for this part, remember that this is equal to 1 over C2, then here what I obtain is that these two summatories, which are exactly the same as these ones, okay, so we have that these two guys, D1I plus blah 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 V2 D2I, this is equal exactly the same. So now n minus 1 is going to multiply everything and then I have to subtract n1. So this is the final result. So what I obtain is that this expression, since these two parts, this is exactly the same as this one, okay, so these two parts are the same. They are the same. Then obviously the other two parts must be the same. Okay, so what we find is that n minus 1 divided by C1 minus n2, it's equal to n minus 1 divided by C2 minus n1. So I'm going to rewrite everything. I'm going to put this n1 on the left and this n2 on the right, and I obtain n minus 1 divided by C1 plus n1 equal to n minus 1 divided by C2 plus n2. And then in the end, I'm going to divide everything by n minus 1, and what I obtain is 1 over C1 plus n1 divided by n minus 1. It's equal to 1 over C2 plus n2 divided by n minus 1. Okay, the only thing I did in the last step was to divide everything by n minus 1. You can see that the formulas are not exactly the same because Newman has a thing that he likes to avoid these minus 1s because it's usually for large n. So for large n, he doesn't care if we have here an n or an n minus 1. I think that he's right, more or less, but when it's useful to simplify things, okay, let's go for it. But if it's not so important here, I mean, what if I write an n minus 1? Is it going to make a huge difference if I write n? It's not, so I prefer to write it like this. And that's it, that's the final result.